Very happy to be here. Okay, I think that's fine. Yes, so today I'll be talking about hypergraph matchings, avoiding certain submatchings. I should say that this is joint work with Luke Postal at the University of Waterloo. And so I should probably define some of the words in the title just to make sure that we're all on the same page. So I'm going to start out talking about hypergraphs. So have all of you heard about hypergraphs before? Graphs? Okay, let's just make sure we're all on the same page. So a hypergraph, okay, so maybe first of all, a graph is going to be a pair of some ground set V that we're going to call vertices or nodes, and some edge set E consisting of pairs of vertices. So in general, we could generalize this notion and instead allow for subsets of the vertex set with possibly more vertices. So we have some ground set V, and we're taking different subsets of the ground set, and I'll call these edges or hyperedges. And if we have the special property that the size of each edge is k, that each edge contains exactly k vertices, this is what I'm going to call k uniform. If I say k bounded, I mean that all of the edges have size at most k. So for instance, this is an example of a free uniform hypergraph. And if we put k is equal to 2, this sort of coincides with our notion of being a simple graph where all of the edges contain exactly 2 vertices. So this is sort of the natural generalization of graphs. And in this context, so perhaps you've heard about matchings in graphs. If not, we can talk about that as well. But we have this notion of a matching in a graph or in a hypergraph, and we're taking a subset of the edge set where every pair of edges, every pair of distinct edges is disjoint. They don't share any vertices in common. So for instance, in the land of graphs, so this is a graph, and we can throw in matchings. I mean, the set of no edges is kind of a silly matching. Taking any one edge is a matching. But for instance, here, we have a matching consisting of these 2 edges, and the same is true in hypergraphs. We can take sort of the larger edges, but we need the property that if we look at any pair of edges, they are disjoint. So that's what I mean by a matching. And kind of the natural question is, can we find large matchings in graphs and in hypergraphs? And this is a hard problem. This is a difficult problem computationally. It's NP hard to find maximum matchings. And in particular, one of the natural questions is, when do we have a perfect matching? So when can we find something like this, where every vertex is contained in one and exactly one of the edges that we've selected? Or large matchings. So it might not be clear a priori why this is an interesting question, but it turns out that a lot of problems from different areas, and we'll survey a couple different applications in this talk, can be written as an auxiliary graph or an auxiliary hypergraph and taking matchings, finding large matchings in this setting. So things that people care about can be written in terms of finding matchings in certain hypergraphs, or as the name suggests, matchings avoiding certain forbidden submatchings in large hypergraphs. So sort of the analogous question, so instead of taking a set of edges where no edges intersect, we could ask about so-called independent sets. So here, what is an independent set? So instead of selecting edges, we are selecting vertices. So for instance, this is an independent set, so it's a collection of vertices that do not span any edge or span any hyperedge. maybe a more interesting independent set. We could take these two vertices, for instance, and you might wonder, what is the appropriate notion in a hypergraph? Probably you've seen independent sets and graphs before. Well, in a hypergraph, it's the same thing. You don't span any edge, but you could take several vertices from one edge. You just don't want to take a complete edge, if that makes sense. So it's a subset of the vertex set that doesn't span any edge of your hypergraph. And here we also care about large independent sets. You can also encode a plethora of problems as independent sets in hypergraphs. We have a notion called the independence number of a hypergraph. So that's the size of some maximum independent set in our graph. So we care about finding large independent sets in general. And why stop at one independent set? We could actually ask to decompose the vertex set into independent sets, so actually partition the vertex set into independent sets. And here we are asking about the fewest number that we would need to do so with. So you could assign every vertex in a graph to be in its own independent set, but that's a bit wasteful to actually have n colors. But the natural question is sort of, what's the optimal way we can do this? What's the smallest chromatic number of the graph? So I'm going to call chi of g the chromatic number of the graph. So you can think about decomposing the vertex set into independent sets. Likewise, you could ask about decomposing the edge set into matchings. So graph coloring, of course, is a very old area of graph theory with lots of applications, including to things like statistical physics. So today, we'll see why this is relevant in just a minute. So I wanted to define quickly a generalization of graph chromatic number as well. So again, a coloring of a hypergraph, we're assigning colors to the vertices where we don't have what we call a monochromatic edge. So there's no edge where all of the vertices are receiving the same color, or equivalently, each edge contains at least two vertices of distinct colors. But there's a generalization of coloring, and of course, chromatic number is sort of the smallest k that you can do this with k colors. So you could ask, however, what if we want to sort of assign a palette of plausible colors to each vertex, and then restrict our attention to colorings where each vertex is coming from the list. The color assigned to each vertex is coming from the list L of V. And so there's sort of a generalization of list chromatic number where this is the smallest k, where you can do this no matter how you assign your list of k colors. So obviously, if you assign k different colors to each vertex, your job is pretty easy. We don't have to worry. But if you assign this list of the same k colors to each vertex, then you see this is actually equivalent to coloring, right? If you have a k chromatic graph and you say, well, I'll give each vertex a list of k colors, then we should, in theory, be able to find this coloring. So we get sort of an obvious bound that the chromatic number is related to the list chromatic number, namely it's upper bounded by list chromatic number if we assign 1 through chi of g colors to all of the vertices. So this will come up in a minute. I just want to make sure we're all comfortable with the notation and comfortable with the concepts. So are there any questions before we get on to the next portion of the talk? Okay, great. So we want to avoid certain submatchings. So let me just ask a very, very general question for a moment. So what if we are in a situation where we have a hypergraph and we want to find a large matching? So here I mean perhaps perfect or perhaps almost perfect, like a very large matching. But what if we put restrictions on what these matchings can look like? In particular, what if we do not allow them to contain certain submatchings? So this is just a very broad question. So motivated by this question, I'm going to introduce a definition. So we are going to start with a multigraph G, a multi-hypergraph G, and we are going to define what we're calling the configuration hypergraph for this graph. So maybe I'll write this definition on the board so we have it for later as well. But we are going to, so we have our starting graph or hypergraph G, and we want to define H as our configuration hypergraph. So this is the key definition for the talk. By encoding the edges of our original graph as vertices, so the vertex set of H is going to be equal to the edge set of G, and we are going to encode matchings as edges. And for technical reasons, I'm not going to care about the empty matching, and I'm not going to care about matchings just consisting of one edge. So we're going to assume our matchings are interesting and have size at least 2. So this is what I'm going to call our configuration hypergraph. So we're sort of dealing with this auxiliary hypergraph. And why is this relevant? Well, if we can find a matching of G, it's H avoiding if it spans no edge of H. So if we think about taking a matching in G, all of a sudden we're looking at edges in G, a subset of the edges of G, and we are H avoiding if we span no edge in H. So we're encoding potential conflicts or the things that we want to avoid here. So this is sort of the key definition. So coming back to our question, what are we really doing here? Well, there's this notion in graph theory of a line graph. So thinking about the line graph of a graph, what are we doing? Well, the vertex set is the edge set, and we are encoding incidences. So we're throwing in an edge. So this is an honest to goodness graph. This is possibly a hypergraph. And we're throwing in an honest to goodness edge if the intersection was non-empty here. So we're encoding the incidences in the hypergraph in this graph. And this is a very old notion. This is a notion that's familiar. So we are interested in finding large matchings in a hypergraph G. But we're really interested in finding bounds on the independence number of L of G union this configuration hypergraph. So more concretely, what restrictions would we need to put on G and H so that the independence number of this has almost the minimum of the independence numbers of the two things? The independence number, so it's the size of a maximum independence set. So we could be even more ambitious. So instead of just finding one matching that avoids H, why don't we actually try to decompose the edge set into some number of matchings that all avoid H? Well, this is a very ambitious question. So maybe let's say almost decompose. Let's add some error. So even finding perfect matchings in general is hard. Let's decompose these things into large matchings that avoid H. Well, this becomes a question about the chromatic number. So instead of looking at the independence number, we're looking at the chromatic number of this thing. So under what conditions does the chromatic number have almost the maximum of the chromatic numbers of the two things? So I just want to state a couple of definitions quickly, and I'll state our main result, which is a bit technical, but then I'll backtrack and explain why we actually care about these things. So we have a couple of definitions from graph theory. So the codegree I'm going to define as the number of edges that two vertices sort of jointly extend to. So we have a graph or a hypergraph, and we have some vertex u and some vertex v. We're interested in the number of edges that these two fixed vertices jointly extend to. The girth is going to be the smallest integer for which the hypergraph has a cycle, and the I degree is just going to be the number of edges of size exactly I containing V. So one of the sort of complications here with this configuration hypergraph business is the matchings that we might want to forbid might have different sizes. So the thing we're looking at might not be a uniform hypergraph anymore, and that's actually going to be a large part of the difficulty in actually doing the computations in our thing. So, okay, this is a bit technical, and we'll go through it and explain sort of what's happening here. But in general, we have a situation where we have some hypergraph, and it's R uniform on n vertices with bounded maximum degree, bounded codegree in terms of the maximum degree. And we have found this configuration hypergraph of G with the things that we want to forbid. And we are going to say that there are no cycles of length 3 or 4, and that each edge contains at most G vertices, and there's some bound on the I degrees. So then we have some upper bound on the chromatic number, and it's going to be some value times the maximum degree of the graph. So this is a bit technical, and we'll go through it a bit carefully in a few minutes. But I also want to point out sort of the reason I introduced list chromatic number is it's actually a bit harder to show that the list chromatic number is also upper bounded by this amount. And there's a lot of power in this statement, and this will generalize a lot of known results as well. But if you prefer to think of the chromatic number, it's true for the chromatic number as well. So what's the point of this? Well, the point is that this is actually a very powerful theorem because it's generalizing two streams of research that were thought to be distinct and unrelated. So namely, when the edges of L of G are empty, or when the edges of H are empty, these types of results, this meta theorem, were studied individually before now and thought to be distinct things going back to the 80s. So let's really delve into that. So what if H has no edges? So maybe this seems a bit silly, but indulge me. Let's say that this configuration hypergraph has no edges. We're not restricting anything. We're just trying to find matchings. Well, we have a bit worse codegree assumptions, but morally, this is saying something similar to the following theorem from the 1980s. So if G is an R uniform hypergraph with bounded max degree and bounded codegrees, then the chromatic number of the line graph is equal to 1 plus little o 1 times the max degree. So stated in other languages, you're looking for large matchings in certain other hypergraphs. Yeah, Ben, did you have a question? Oh, sure. So yeah, maybe I should have put it here with the configuration. So L of G was the line graph, and so the vertex set is equal to the edge set of the original graph, and you're encoding the incidences in the hypergraph. This is an honest to goodness graph, but you're taking in some hypergraph G, and the edge set of G, L of G, is going to be UV, such that U intersect V is not empty. So they have some vertex in common. So you're encoding the incidence as. Yes, so it's, well, it's related to the matching number, which I didn't define, but it's sort of the analogous thing to the independence number, the size of a largest matching. So you could rephrase all of this and think about finding a large matching in some R-uniform hypergraph with bounded codegrees. And so there are various versions of this theorem. So sort of Rodel had some original version, Pippinger in an unpublished work has a subsequent one, Pippinger, Spencer have this, and Kahn even showed chi-L, the list chromatic number, in a really famous paper, which proves asymptotically the list coloring conjectures. This is a really, really celebrated result, showing this instead of for chi-L of G. So these things are really, really fundamentally important. And maybe actually I could say a few words about nibble type methods that might be worth saying something as well if you're not familiar with them. So Alone and Spencer has a really nice sort of subsection about them that I'd encourage you to look at as well. But sort of the idea here is, in general, it's really difficult to find a large matching in a hypergraph, right? So it's difficult to find a large matching in a hypergraph, even with very mild degree and codegree restrictions. But for applications we'll see later, this is a very natural question and one that's actually important in a lot of areas. I mean, there's even work with like gaps in the primes and things that uses Pippinger, Spencer. You can encode things from number theory, from lots of different areas. And some innocuous statement about matchings in hypergraphs or chromatic number in line graphs of hypergraphs becomes quite powerful and quite interesting. So maybe let me just wave my hands a bit and try to explain what the nibble is if you haven't seen it before. So instead of in one go trying to construct some structure, whether it's a large independent set or a large matching, let's just think about matchings for the moment. So say you have your hypergraph and you're trying to find a large matching. So not a perfect matching, but one that's like all but some little one of whatever size matching you would expect to find. Well, we could, instead of trying to find a matching in this whole graph, take edges independently, uniformly at random with some probability depending on the maximum degree. So we take some little chunk out of the graph and we want to digest that. Instead of trying to take on the whole graph or the whole hypergraph, we take a little nibble out of it. And then we have to do some work here, but essentially we want to say that the edges don't overlap too much. So we could take a lot of these and throw them into a matching. And then we just delete all of these vertices from the graph. So meaning if there were some edges that kind of overlap as well, we could get rid of those as well. And then what's left, I'm claiming, well, it's obviously bounded max degree and bounded codegree, because the thing that we had before was, and we're only deleting edges, but I'm claiming it has a lot of other properties. So we have this iterated algorithm where we're successively taking bytes out of this hypergraph. So the magic is we can go again, even having deleted these things, we want to argue that there are enough vertices left that we didn't delete, and the edges have certain properties that we would expect, that we can do this nibble again and again and again till we get to something where we can just finish. And so we get an almost perfect matching. So this is sort of Rodel's original idea, proving the Erdős-Hánányi, the approximate version of the Erdős-Hánányi theorem, which I'll talk about in a minute what his hypergraph looked like. But it's a really cute approach, and it's surprisingly powerful, this iterated algorithm, and it has a lot of interesting applications. So one stream of research historically has been these nibble type methods, predominantly used in design theory, but also coming up in things like number theory. But if we, it might seem silly, but say that the list graph of G has no edges, well then we're saying that there are no incidences, right? That's what it means for the line graph to have no edges. There are no incidences. So we would have a matching. So we're going to end up in the realm of Itai-Komolosh Spencer-Semiretti. So another seminal stream from the 80s that historically has attracted a lot of attention and been very well studied. And so here we have our uniform hypergraphs on n vertices with no 3 cycles and no 4 cycles and bounded max degree. Then we're saying something about the independence number, finding a large independent set in this setting, which in and of itself is also an interesting question. And there have been a number of results. So all this plus GERF at least 3, all this, but instead of for one independent set, finding a coloring, all of this, but instead of GERF at least 5, some bounded codegree condition, plus mixed uniformity. And our theorem will do all of this as well. But with the caveat that we have to be careful here, we aren't doing GERF at least 3, we're doing GERF at least 5, but we do the other things. So maybe let me just say a few ideas about the proof and then end with a couple fun applications. So in general, there was like this really nice survey article on the Nibble method, kind of talking about 2 distinct threads of research, because fundamentally we kind of think of vertex coloring and edge coloring, of which finding an independent set and finding a matching are fundamentally related, as very different and sort of having been developed in parallel. And we're kind of saying these things maybe shouldn't be thought of in parallel, that people are reinventing the wheel quite a bit, and these all follow from some big meta theorem. So we're tracking weighted degree because we run into this issue because our matchings, our forbidden submatchings, could be different sizes. So we don't have a nice uniform thing that we're working with. That's really complicating things. We are simultaneously doing some sort of nibble process on the original G or L of G and with H. And somehow the calculations all work out nicely together, but it's not clear a priori that it should be true. We introduced a new linear Talleyrand inequality to concentrate things, to show that we can actually do this iterative process, that the things at each step are like we would want them to be, and then we end with the local lemma. So I should mention this is all on arXiv if you want to read all the details as well. It's like 50 pages, but we include all the details, especially with this Talleyrand inequality, in the appendix. So our main application, our sort of original reason for thinking about these, wasn't some general question in the theory of hypergraph matchings. It was some very concrete, very fundamental problem in combinatorics and number theory. So there's this notion of Steiner systems. So let me define this. So an NQR Steiner system, we are thinking of taking Q element subsets of a ground set. So we're taking Q element edges of some ground set with the property that any fixed R element subset of the vertex set is contained in at most one edge. So this is maybe a bit of a mouthful. And we say that this is a partial one, and if each is contained in exactly one, or the largest size possible, this is a full Steiner system or an NQR Steiner system. So let's look at an example for a second. So we can think about the Fano plane, for instance. So when n is equal to 7, and r is equal to 2, and q is equal to 3, we're thinking about a 3 uniform hypergraph on 7 vertices, where we can throw in an edge for each line in the Fano plane. And looking at the properties of the Fano plane, we see that for every pair of vertices, it lives in exactly one line. So this is a 7-3-2 Steiner system. But if you have the property that the R element subsets live in at most one Q element subset, This is a partial one. So the largest possible ones are going to be full Steiner systems. And when Q is equal to 3 and R is equal to 2 is sort of a special case. These are called triple systems. And these are really important in number theory, for instance. And there are a lot of really important questions in design theory about these objects. So maybe let me touch on a couple important conjectures that have recently been solved. And there are certain obvious necessary divisibility assumptions that we're going to assume. A natural question is, when do these things exist? So one of the first problems from the 1800s in design theory is, when do these things exist? And the conjecture was, when the obvious necessary assumptions hold, we can actually construct these if n is sufficiently large. And there's been a lot of work on this conjecture. I mean, this conjecture, or even just a case of it, was sort of the motivating conjecture that led to the nibble technique in the first place. So for triple systems, Kirkman showed this in the 1840s. When R is equal to 2, this was solved in full by Wilson. But then the nibble technique showed the approximate version, and the full conjecture was only recently solved using some sort of randomized algebraic construction and purely combinatorial techniques quite recently. And this was a very, very big deal in the combinatorics community. But this is now fully resolved. So what's next? What else can we say? Well, there was this other conjecture about triple systems. So in general, if we have a partial Steiner system, we are going to find a JI configuration as IQ subsets spanning at most J elements. So again, we're thinking of these as vertices and these as hyper edges. So as a set of Q hyper edges spanning at most J elements. And this was observed by Erdős in the 70s that even triple systems have a lot of structure. We're guaranteed to have a 4-1 configuration if we have enough vertices, a 5-2 configuration, and so on. In general, an I plus 3I configuration. But then he asked, but what if we want to think about I plus 2I configurations? So he conjectured that for every integer, for n sufficiently large, we can find a Steiner triple system with none of these configurations for I between 2 and G. So this is a very famous conjecture of Erdős. So let me reformulate this, because this is a bit of a mouthful. So we had this notion of girth for hypergraphs before. Let's define a notion of girth for Steiner systems. So this is going to be the smallest g, for which we actually have a g plus 2g configuration. And in this language, what is Erdős asking? Well, he's asking for us to find the existence of triple systems of arbitrarily high girth. And this kickstarted an entire area of combinatorics, high-dimensional designs, high-dimensional combinatorics. You can try to think about finding high girth versions of a lot of existence problems and really try to say something about the structure of these things or the typical structure of these things. Well, this has also recently been solved. So I'll say a few words. The approximate version was shown fairly recently by Bowman-Warnke and Glock-Kuhnlo-Ostis using sort of greedy randomized approaches, but it was solved in full using kind of similar techniques to the proof of the existence conjecture, iterated absorption, by this group of people in January. And this is where we really got interested, because we asked, well, can we simultaneously generalize Erdős's conjecture and the existence of Design's conjecture? So these things are known in full. What can we say about Steiner triple systems with arbitrarily high girth in general? And of course, the answer is people have thought about this. So there's a natural notion of what high girth looks like. So in this language, what do we show? Well, we show the approximate version. So showing the full thing would be also very interesting, but we show the approximate version using our method of matchings avoiding forbidden submatchings. So they ask, can we find NQR Steiner systems of arbitrarily high girth? And this formally is what we show. So I'll mention here, this would be the size of a full NQR Steiner system. So we show there's a partial one of fairly large size with none of these as sub-configurations. And here, the error term, we're very proud of this error term being a polynomial in N because it is what you would need to show in order to show the full conjecture. This is the approximate version that you'd need in order to have a hope of proving the full conjecture. So it would be really nice if this full conjecture were solved. So I should mention another group independently announced very similar results within a couple weeks, and they had independently come up with this notion of configuration hypergraph. It's not such a deep notion once you see it, but it's sort of the magic that makes this all work. I will say a few things though. Their approach is also one of these randomized greedy approaches. So they fundamentally are not getting all of the same results we are. So they're not able to get a number of the applications that we do. And there is sort of a trade-off though. Ours is a nibble approach, so we're not getting some of the counting results that they get. So the applications they care about, they're able to do, and the applications we care about, we're able to do. But there are a lot of results that both of these solve simultaneously. Yes, so they also get this sort of error term. Their proof can sort of be viewed as a generalization of Bowman and Warnke's approximate version. They use similar techniques to their proof, whereas ours could be viewed as a fundamentally new proof to Bowman and Warnke's results as well. But they also get the error term that you'd need in order to prove the full conjecture. So that's really nice. So let me just say a few words about, so you might be wondering, why are we mentioning Steiner systems? Why are matchings coming up at all? If you saw the original proof by Rodel, it would be very clear, but I'm assuming most of us have not. So why don't we go through that? And then I'll touch on a few applications because I see I'm running short on time, but I think maybe this would be a nice thing to run through together. So, all right, we were talking a lot about matchings and finding large matchings in hypergraphs, almost perfect matchings in hypergraphs. Let's define the following hypergraph. So again, what were we doing with Steiner systems? Well, we cared about Q element subsets that contain sort of these R element subsets. So for each R element subset, let's put a vertex down. So when we're thinking about the Fano-plane example, for instance, you can pick the pairs of vertices that would live on a line, and then we're going to throw in an edge for each Q element subset. So in the Steiner system, one of the potential Q elements that we could pick. So we are going to pick R element subsets that lie in a particular Q element subset. So for each Q element subset, we're thinking about the R element subsets that contain that Q element subset. Sorry, the other way around. So we have, let me maybe draw a picture. So like for the Fano-plane, right, so we have N, Q, R, and for the Fano-plane, we were dealing with something like 7, 3, 2. So our vertices here, we would be picking all pairs of vertices from, say, 1 through 7 as our vertex set in this auxiliary hypergraph. And then for each potential line, for each 3-element subset, the ones that we're taking in our collection for Steiner systems, we are going to think about all the 3-element sets that lie there. So For instance, if we're thinking about the ground set being 1 through 7, then you would, for instance, throw in this as a hyperedge. So you have Q element subset 1, 2, 3, and it contains 1, 2, 1, 3, 2, 3. Likewise, 1, 2, 4. You would throw that in, and we're putting in all of them. So what's the point of doing this construction? Well, when we take a matching in this context, what are we doing? So when we take a matching in this context, we are selecting some number of Q element sets, right? And that's what we want to do with a Steiner system or a partial Steiner system. But they're Q element sets with the property that each R element subset lies in at most 1. So a matching in this hypergraph, right, if we select this edge to live in our matching, then we're forbidding this edge to live in our matching, right? So from the perspective of the 2 element subset, it's going to live in at most 1 edge, right? And we're selecting which edges we are going to take, which Q element subsets we're going to take. Is that clear to everyone? So a matching in this context is exactly going to be a partial Steiner system. And if we balance our divisibility conditions just right and actually achieve a perfect matching, then this would be a full Steiner system. Was there a question? No. Okay. So once you see it, this is exactly the construction that Rodel used, and it's what he was doing the nibble with. And when you find a large matching in this hypergraph, then you're done. So let's just double check the conditions. So we wanted it to be regular or bounded max degree with bounded co-degrees. So let's just check those. So I'm saying this is a uniform hypergraph. So why is this? Well, each edge is kind of encoding a Q element subset, and we're picking all our element subsets that could live in that Q element subset. So there are Q choose R elements in each hyper edge. So we are uniform. And we are also regular. So we have bounded max degree, we're actually even regular. So why is this? Well, if we think about from the perspective of the R subsets, how many Q subsets they could live in, well, we have itself, and then we're thinking about the ways that we could extend it. So there are n minus R other vertices, and to extend to a Q element subset, we would add Q minus R other elements. So it lives in n minus R, choose Q minus R edges. So the degree is this. And now, what about the co-degree? Well, if we think about 2 distinct two element subsets here, R element subsets in general, and think about how many edges these are jointly extending to, well, we really worry about when the co-degree is too large. We want bounded co-degree. And what's the worst case scenario? They're distinct. So the worst case scenario is that they're all the same except for one element, that we've picked 2 R element subsets that intersect in all but one element. So in general, they have R plus 1 elements in their union. So we have n minus R plus 1, choose Q minus R plus 1 common edges there. That's the co-degree, which we see is some constant times D. So all of this goes through fine. You could run Pippinger-Spencer on it to get a large matching. Rodel get a large matching. And that is their de Shannani conjecture, is that you have these almost Steiner systems, these partial Steiner systems of large size. But in our context, we are throwing in more restrictions. So we're doing something really similar, but we are encoding these Gerf conditions as forbidden sub-configurations. So maybe in the interest of time, I'll spare you the details, but just looking at the definition of Gerf, you can check that all of the conditions on H are satisfied, and therefore we can get a partial Steiner system of very large size that has high girth. It has none of these forbidden subconfigurations. So that's sort of the takeaway there. And maybe let me mention a couple of nice applications. Yes? Yes. Could you repeat your question? Sorry. Yeah. It's an inequality. Yeah, you can encode that in the little one, but it's a upper bounded by this. So you can find not only one large matching, but you can actually decompose your graph into approximate Steiner systems. Is kind of the punchline here, which is something that people hadn't even asked. Maybe it's obvious to people, but it's sort of a nice corollary, is that not only do you get one large matching, but you can decompose into a number of matchings, which then gives you a decomposition into higher Steiner systems. Did you have a question? Yeah. So in general, yes. So in general, thinking about chromatic number of a hypergraph, you're never going to do better than D, because you could think about a vertex and then all the edges incident to it, and you'll need at least D. Yes. So you're in particular linear, you have a high girth. So we can go back. Whoops, no, we're going forwards. Sorry, it was further back than I remember. Yeah. So yeah, you get like, well, this is the number of vertices of H, but here H we're thinking of as our configuration hypergraph. So you have n log d over d to some power, where this is the uniformity of our hypergraph. But you're going to have a natural bound arising from the max degree. Okay, so maybe in the interest of time, we're almost out of time. Let me maybe skip to the end then. And if there are further questions, I'm happy to chat. But yeah, the main punchline is by using this notion of the configuration hypergraph and running the two nibbles simultaneously, you see that actually these are both morally special cases of some larger result. And there are a lot of applications, and just this result that I mentioned earlier gives you the Steiner triple systems of high girth, but we have a bipartite version, which at first glance maybe doesn't look so impressive, but it actually is a stronger statement, implies this main result. And this bipartite version gives you a lot of really nice things, including rainbow matchings, high-dimensional Latin squares, high-dimensional permutations. There are a lot of different versions. And sort of my main takeaway here is that in this realm of high-dimensional combinatorics or high-girth combinatorics, in general, any setting where you have a Rodel-Nibble type result, you could ask about a high girth analog if you find the right definition, and this sort of theorem will give you not only the high girth version, but in fact something a bit stronger, approximate decompositions into these high girth systems. So thank you for listening. This went by really quickly, but yeah, I'm happy.